43 million tonnes of lithium, buried under an abandoned German gas field, one of the largest deposits in the world. That was the headline. If you read the MSN article, it sounds like Germany just stumbled onto a buried Saudi Arabia of battery metal, a hidden treasure waiting to be pumped out of an old gas reservoir and poured straight into electric cars. But here's the part the headline doesn't tell you. This isn't a giant underground lake of lithium brine like Chile's salt flats. It isn't a hard rock pegmatite mine waiting to be drilled and blasted. It's not even a conventional geothermal system with roaring hot water rushing through permeable rock. It's something far more subtle. The lithium is dissolved in extremely salty formation water trapped inside deep Permian sandstones and volcanics, rocks that were deposited roughly 290 million years ago. Those rocks sit 3 to 4 kilometres underground. They are hot, they are tight, and in many places, they barely let fluid move at all. The 43 million tonnes figure is not a measured, flowing reserve. It's a probabilistic estimate of lithium in place, the amount dissolved in brine across a vast basin, assuming ideal conditions. And the same scientific assessment that supports the existence of that lithium also makes something very clear. Most of it sits in low permeability rock. So does that mean the headline is wrong? Not exactly. But it does mean the story is far more geological and far more complicated than the media version suggests. And once you understand the geology of the Altmark Rotliegend, you start to realize this isn't just a lithium story, it's a deep time story. It's a story about desert basins, volcanic ash, mica minerals breaking down at high temperatures, and brines evolving slowly over hundreds of millions of years. So let's go underground. If you travelled back to the late Permian, northern Germany would not look anything like it does today. No forests, no cities, no North Sea oil rigs. Instead, you'd find a vast arid basin, the southern Permian Basin, stretching across what is now northern Europe. This was a desert world. Wind-blown sand dunes migrated across dry plains. Seasonal rivers deposited fluvial sands. In places, ephemeral saline lakes formed, evaporated, and reformed. And scattered across parts of the basin were volcanic centres shedding ash and lava into the sedimentary system. These sediments are what geologists call the Rotliegend. In the Altmark region, the upper Rotliegend is dominated by sandstones interbedded with volcanic material. Beneath them lie lower Rotliegend volcanics, acidic volcanic rocks enriched in lithium-bearing mica minerals. That's where the real story begins. Lithium doesn't just appear in brines, it has to come from somewhere. In this case, the source is mica, minerals like muscovite and biotite embedded in volcanic clasts and basement rocks. These micas contain lithium within their crystal structure. Now imagine burying those rocks beneath kilometres of sediment. As burial continues, temperatures rise above 120 degrees Celsius, fluids circulate, the chemistry changes, micas become unstable, they begin to alter. Chloratization and dissolution processes break down the mica structure, releasing lithium into the surrounding formation water. That water is already salty, extremely salty, because this basin has a long history of evaporite formation and brine evolution. Over time, lithium accumulates in the brine, not in one place, not in a single pool, but throughout a connected aquifer system spanning large parts of the basin. The measured average lithium concentration in Altmark reservoir brines is around 375 milligrams per litre. For context, seawater contains about 0.17 milligrams per litre, so this is more than 2,000 times richer than seawater. That sounds impressive, and it is, but concentration is only part of the equation. The brines sit at depths of roughly 3,200 to more than 4,000 metres. The reservoir rocks are hot, mineralised, and in many cases, tight. Some Rotliegend sandstones have decent porosity and permeability, especially in ancient dune and erg margin facies, but large portions of the basin centre consist of play deposits and interbedded claystones with permeability below 1 millidarcy. That's effectively impermeable on a production scale. So while the lithium is there, moving enough brine through this system to extract it economically becomes the real challenge. This is where the giant field terminology comes in. From an oil and gas perspective, the Altmark gas field was indeed giant. It has produced hydrocarbons for decades, and volumetrically, if you calculate the total pore space across the basin and multiply by lithium concentration, you can reach enormous in-place numbers. 25 million tonnes of lithium carbonate, equivalent at a median estimate, with high-end scenarios exceeding 60 million tonnes. That's where the headlines come in, but here's the technical nuance. Those numbers assume open boundaries, uniform distribution, and do not represent recoverable reserves. They are geological capacity estimates. The recovery factor, the percentage of lithium you can realistically extract is modelled between 0 and 10%. If the recovery factor is closer to 2%, the practical output shrinks dramatically. And then there's the permeability. The most lithium-rich intervals are associated with Permian deposits that were never intended to be high-flow geothermal reservoirs. Unlike the Upper Rhine Graben, where geothermal lithium projects operate in a fractured, high-permeability system, the North German Basin's Permian rocks often require stimulation to enhance flow. Stimulation means hydraulic fracturing. And historical simulation tests in similar formations have shown complex interactions between rock, brine, gas, and technical infrastructure. Productivity declines can occur. Scaling and clogging can become problems. Highly saline fluids at high temperatures are chemically aggressive. This is not a simple pump and filter scenario. There is also a fascinating geochemical debate about lithium migration pathways. Some studies suggest deep faults may have acted as conduits, allowing lithium-rich brines from permo-carboniferous rocks to migrate into overlying Zechstein carbonates. Others point to in-situ leaching within re-sedimented volcanic clasts in the sandstones themselves. Is the lithium mainly generated locally, or is it partly introduced from deeper systems? The answer affects sustainability. If lithium is primarily the result of ancient leaching and is not actively replenished, then production becomes a finite extraction problem. If ongoing water-rock interaction contributes lithium over time, the dynamics change. These are not minor questions. They define whether the system behaves like a mine or like a renewable resource. And then there's the geothermal coupling issue. In many lithium from brine projects globally, lithium extraction is paired with geothermal power production. You pump hot brines to generate electricity, extract lithium, and re-inject the fluid. But in the Altmark system, the highest lithium concentrations are not necessarily co-located with the most favourable geothermal production characteristics. Some Mesozoic reservoirs have better permeability but lower lithium grades, often under 10 milligrams per litre. So operators face a choice: chase lithium concentration in tight Permian rocks, or chase permeability in younger formations with less lithium. The geology forces trade-offs. From a basin perspective, what makes the Altmark scientifically compelling is not just the lithium volume, it's the geochemical coherence. The brine compositions indicate large-scale connected processes. The enrichment pattern aligns with mica alteration. The distribution matches Fassi's architecture of the Rotliegend. This is not a random anomaly. It is the predictable outcome of burial, volcanism, and brine evolution in a desert basin sealed by evaporites. And that makes it geologically elegant, but elegance does not guarantee economics. If you are a layperson reading the headline, you might imagine lithium sitting in an underground cavern waiting to be pumped out like oil. If you are a reservoir engineer, you see questions about transmissivity, flow rates, scaling risk, and DLE efficiency. If you are a geochemist, you see mineral alteration pathways and isotopic signatures. If you are a policy maker, you see energy security. All those perspectives are valid, but the true story lives in the rock. Altmark is not a sudden discovery. The elevated lithium concentrations were identified decades ago, even in the 1970s. A direct lithium extraction plant was nearly commissioned in the 1980s. Political and economic changes shelved it. Now, with lithium demand surging, the geology has returned to relevance. And the geology hasn't changed. It is still a deep Permian desert basin. It is still composed of wind-blown sands, volcanic fragments, and ancient saline waters. It still requires moving fluid through tight rock. The MSN headline tells you Germany uncovered one of the world's largest lithium reserves. The science tells you Germany has a very large lithium in brine resource, generated by Permian mica alteration, stored in deep Rotliegend aquifers, technically challenging to produce, and subject to significant recovery uncertainty. Both statements contain truth, but only one tells the full geological story. And in geology, the full story is always more interesting than the headline. I hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.